We are going to begin talking about charge in a quantitative way now. So the first thing is that you're going to see the word Coulomb a whole lot in this class. It refers to a person, it's going to refer to an equation, it's going to refer to a type of force, and right now it's going to refer to a unit. So the SI unit of charge is the Coulomb, which is abbreviated capital C. If you write lowercase c, that's fine as well. So the charge of one electron, which we call E, so it's the fundamental quanta of charge, is 1.6 times 10 to the negative 19 C. So what you should think about is that one electron has very, very little charge. So 1 coulomb of charge is a lot. 1 coulomb of charge is a huge amount. Now, typically, if we talk about a charged object, the excess charge we're going to be talking about is 1 to 100 nanocoulombs. Now, what you might remember is that a nanocoulomb is going to be 10 to the negative 9, right? So this is 10 to the negative 9c. So if you have a calculation and you calculate that the charge on a balloon is 10 to the negative 10c, 10 to the negative 8c, that's all reasonable. If you get 10 to the positive 8c, that's way too much charge. That's definitely not happening. So it's a little awkward to get used to this since coulombs is probably a new unit for you, but you should expect to see charge that's in the nanocoulombs range, so 10 to the negative 9c. So here is what's going to be called Coulombs Law. Now note that this is a force, but note that there is not a vector symbol here. Why? Because there's no direction. Now, depending on what textbook you look at, you might see this written in a few different ways. We could actually write this as having a vector symbol and having a direction of r hat, which means it's in the radial direction. But that actually gets a little bit confusing because then you have to say, well, radial from what? So what the approach we're going to take is to not explicitly state the direction in the equation, which means this is only calculating a magnitude. Note that there are absolute value signs around each of the charges. Why? That means both of these need to be positive values. If we're calculating the magnitude of the charge, the magnitude of the force, it cannot be negative. So even if you have a negative charge on your object, don't keep that minus sign when you go to calculate this. So this is an equation, you plug some numbers in, we'll talk a little bit more about that. The first thing you need to know about Coulomb's law is that this is only applicable to point charges. What is a point charge? It is a charge that literally has no spatial distribution. In mechanics, we talked about the particle approximation, and so point charges is another way of just saying particle. So you can't use Coulomb's law if we're talking about the force between, for instance, two planes of charge or two rods of charge. We have to be able to think about our objects as point charges in order to use this. One of the most common mistakes students make in electrostatics is that they use Coulomb's law when it's not applicable. So please keep that in mind. So conceptually, okay, we can use this to calculate a numerical value of the force between two point charges. And we do need two charges for this. R is going to be the distance between the two charges. Because they're point charges, we don't have to worry about between their centers versus between their edges. They're point charges, they have no size. So there's then this constant out in front. So note that E naught, or epsilon naught, is a constant. It's not a variable, and it has this value. So also note the units here. We have Coulomb squared divided by Newton's meter squared. So you have a meter squared coming from this distance, you have Coulomb squared coming from these two charges, and so that leaves a Newton, giving you the correct units of force. So this is a value you plug in. You're also going to see this written in another way. You might see K, Q1, Q2 over R squared. And note that K is just equal to 1 over 4 pi epsilon naught, right? So we can actually have two different values here, and one would be 1 over 4 pi epsilon naught, one would be k. And obviously 4 and pi are also constants. So two different choices of constants. I typically use 1 over 4 pi epsilon naught because epsilon naught comes up in other contexts. This really is the easier way in the long term to do it rather than learning two different constants. So this is a different constant k, but I'm just not going to use it. I'm going to use this version of the equation. So the last thing before we move on from this is that we do need to think about the direction, since forces always do have a magnitude and a direction. And in this case, it's going to be determined by whether you have like or unlike charges. And we've already talked about attractive and repulsive forces. So we know that the force is going to repel or attract the two charges, and that's going to be along the line that connects the two of them. So not necessarily up, down versus left, right. It depends really on how the charges are oriented. The other thing to recognize is that there's actually going to be a force of 1 on 2 and a force of 2 on 1, right? So we also have 2 on 1. And these two forces are going to be equal in magnitude, but opposite in direction. These are Newton's third law pair. So repel and attract, that definitely works, but then you need to actually determine the direction. Think carefully about which force you're actually calculating it on, which of your charges you're worried about. So think about that. Lastly, this does behave like other forces, meaning that you can have superposition. You can have multiple forces acting on the same object, in which case you need to think about the net force, and the net force then determines the acceleration. So to talk a little bit more about the directions, we can think about three situations. So opposite charges, we have a positive and a negative, two positive versus two negative. Now in the positive and the negative case, they both repel. So these forces actually point in the same direction. In the opposite case, they're both attractive. So note that the size of these vectors are the same. This is always equal magnitude because the magnitude of the force depends on both of the charges. So Q1 times Q2 versus Q2 times Q1 is the exact same thing. These are literally a Newton's third law pair. So if you remember Newton's third law, that's the idea that every force has an equal and opposite force, but that Newton's third law pair involves two forces of the same type. These are both Coulomb forces, charge forces, that act on different objects. So that works. So this is what we mean by direction of the force. We can always draw that vector, and it's on the line that connects these two charges. So obviously, if the charges were oriented differently, the forces would point in a different direction. We are now to our first problem-solving strategy. So this applies if you can identify your charges as point charges. So you might have some objects that can be modeled as point charges, and that would be the case, for instance, of having two balloons that are very, very far apart. In that case, they're as if they are point charges. But if you have two balloons that are very, very close together, that doesn't work as a point charge then. Make sure that you're drawing a picture and you want a coordinate system, you want to show the positions, and you want to be able to show the force vectors. If you have additional forces at play, so for instance, if you actually have multiple charges, you might want to draw a free body diagram. So do think about that. And this is how we go from whatever the situation is to start actually calculating our problem. So again, make sure that you label everything clearly: positions, charges, distance r. We then are going to use Coulombs law. Here again, the book is using k, but I encourage you to use 1 over 4 pi epsilon naught q1 times 2q over r squared. So we're going to plug values in to get out a value for our force, but you must show the directions of the forces based on your visual representation. And again, you really do want to explicitly state that. And don't draw that little vector symbol above the F if you're not also tagging on the direction. We don't have the vector symbol here because this is just the magnitude. So if you have multiple forces, you actually need to do vector addition. You can do that graphically. at that to give you an idea, and then otherwise you need to break it into components. And again, working with vectors should be a review from what you've studied in the first part of intro physics, so that's something to check now if you feel like you don't remember it or if you never mastered it previously. So again, this is a big problem solving strategy, and it's one that's really fundamental to what we're working with this semester.